Thank you, Samina. So very good morning, good afternoon, and good morning to all. I, Dr. Pallavi Saxena, SSC member of iLEAPS, and Dr. Samina, Project Administrator iLEAPS, welcomes you all on the occasion of our third talk in iLEAPS Global Colloquium Series 2022. So let me introduce what iLEAPS is. So iLEAPS is Integrated Land and Atmosphere Interactions, and it's a global project of Future Earth, which providing understanding of physical, chemical, and biological processes, transport, and transform energy and matter throughout the land atmosphere interface. So the prime purpose of this colloquium is to introduce the scientific society, people with the distinguished and significant work of eminent scientists all over the world. It is a very bright opportunity, particularly to ECRs, to interact with them and establish the bridge between the ideas and the knowledge through this platform. So our third speaker of this series is Professor S.N. Tripathi from Indian Institute of Technology, Kanpur, India. So we are privileged to have Professor Tripathi with us. So let's have a brief introduction about him. Professor Sachchida Tripathi is a professor of civil engineering at IIT Kanpur, where he joined in 2003 and was head of department and coordinator of Center of Environmental Science and Engineering. His research focuses on air quality, climate change, and nuclear reactor safety. The scientific accomplishments and mobilization of human resources through knowledge network of NICAP, MOAFCC have made Professor Tripathi a leading scientist with impactful contribution to India's air pollution challenges. He built groundbreaking, innovative approaches to qualify accuracy, affordability, and feasibility of indigenously built sensor-based network technologies for nationwide air quality monitoring and RTSA. He also set up National Aerosol Facility supported by DAE for nuclear safety studies. He is currently holding a prestigious position of National Coordinator in National Knowledge Network, National Clean Air Program, India. He is also awarded with prestigious Shanti Swarup Bhatnagar Prize and elected as fellow for his contributions to science and technology. Uttar Pradesh government also conferred on him UP Ratna Award in 2018. He was also a distinguished alumnus of Banaras Hindu University, Varanasi, India. He was senior fellow of NASA GSFC and visiting professor of Georgia Tech University, US, Orleans University, France, and Tokyo University, Japan. So today he will be speaking about the aerosols, the double-edged sword for climate and air quality. So about the talk, he will tell the story of aerosols from their role in cloud formation to cloud condensation to other climatic and health effects. It will also discuss India's National Clean Air Program, which aims to reduce particulate matter by one-third by 2024, and combined efforts of higher technical institutions towards achieving NICAP goals by developing scalable monitoring technologies and capacity building. So now I would formally invite Professor Tripathi to deliver his talk and enlighten us with your work. Professor Tripathi, the floor is all yours.
Thank you very much. Thank you to iLEAPS for giving me this opportunity to share some of our work with the larger iLEAPS community. I believe you could also see my slides now, Pallavi. Correct?
No, we can't see.
I opened it. You can't see it?
No.
Now?
Not yet.
No.
So,
okay. Can you see now?
No.
Not yours. We can only see your.
Yeah.
Because I just the way we did last time. I just shared it like that only. I just shared the screen last time, and that's what. That's it.
Yeah, it worked when we did the trial. So
yeah, is the share screen is? Can you see my screen now?
Not yet.
Not yet.
Okay. Can you see now? Yeah.
Yeah. Perfect. Yeah.
Okay. Sorry about that.
It's okay.
It's okay.
Yeah. Okay. Yeah. Can you see now? Yeah. Okay.
Yeah. Perfect. Yeah.
Okay. Wonderful. So, hello everyone. So, basically, I'm going to just give a story of aerosols and how basically it plays the role in this climate system and air quality. And I should tell you that I start with giving some idea about the role of aerosols in the global climate system. And then I'll show some of the work done in India, and then how going from the climate, how aerosols impact climates, then we'll move to the air quality and what's plan government has here to improve air quality and how these technical institutions are supporting this very ambitious plan of government. So good part of the talk, of course, would be India-centric. So let me just, as a primer, I should give you this slide. Some of you who probably know it, but for others who are not from aerosol background, what you see here on the x-axis, you have a variety of different sources of emissions. There are cities, there are rural areas, and there are biogenic sources like forests, and they can emit particle and gases. And what you see on y-axis, from after emissions, the gases and particulate matter or aerosols can spend some time in atmosphere. And then certainly after that aging in the atmosphere, they can act as cloud condensation nuclei, what you see, and through that they can modify cloud, and therefore the interaction of radiation with cloud can also be impacted. And the particles or aerosols, I will use them interchangeably. And when you talk in climate system, you use word aerosols, and now when you go to air quality, particulate matter is something which you use. So we can certainly use them loosely here. And in between, what you see that some of these gases, which we call precursors, and if they are organic gases, they can be precursors for secondary organic aerosols, and they can undergo through a very complex physical and chemical transformation, which are all mentioned here. Some of them could directly be emitted in solid phase. Some of them can, be starting with highly volatile gases, can convert into little volatile gases, and then they can partition into particle. And all these things can happen, and that can also lead to formation of fog. So this is a whole thing is very, very complex, and you see that it's going to play a major role in both you can say the climate system, and can also impact the air quality in a major way. So why are we so interested in understanding the role of aerosols in climate change? Because the major reason is that we want to understand how the climate is changing. And we know that climate change is primarily happening because of the most dominant greenhouse gas, carbon dioxide. And we want to understand that how it is forcing the climate, and we call it radiative forcing. Okay, that forcing translates into some way the change in global temperature what we are seeing. So what we are seeing now is measured, but based on that, we want to develop understanding to predict it. We want to improve our predictability. So then there are other gases which are also greenhouse gases. What you see, these all gases are mentioned here in this table, and all of them have certain kind or amount of forcing they exert on global climate system. And you see there are bars. So this is a table taken from IPCC, Intergovernmental Panel on Climate Change 13. And these bars show you that the basically size of the bar show you how much forcing they are putting. And if you are on the right of 0, that means they are putting a warming. And if it is left, that means they are causing a cooling. Right? And then there are also, you see, there are on every bar, there is also an error bar, which gives you how much uncertainty is there. And what you notice that for the gases, that bars are large compared to the uncertainty. So our understanding of forcing of gases on the climate system is getting better and better. But now if you come to this part of the table, which is highlighted in this red box, and there what you see that there are two other kind of complexity coming to this entire system because of how aerosols interact with radiation and how they interact with clouds. And what you notice that because you have a whole variety of aerosols, they have very different optical properties, radiative properties. Therefore, what you see that the bar is going both on the that means it's called, some of them are causing cooling and some of them are causing warming. So we don't have a very clear idea about that. And the second gray bar, which is because of the aerosols interaction with clouds. And that, if you notice here, is that that causes cooling, but the uncertainty is larger than the size of the bar itself. And that is what these uncertainty, because of the role aerosols play through their interactions with radiation and their interaction with cloud, limits our ability to predict the climate change in a very good way. And that is why we are so interested in understanding the role of aerosols in our this giant, you can say that planetary climate system. So this actually is a very nice, you can see that calculations, and which is illustrated very well in this paper of Ramanathan and Carmichael. What you see that on the left-hand side, you have gases, greenhouse gases, right-hand side, you have aerosols. And that shows that these gases are highly unreactive. So you know that they can stay in the atmosphere for about 50 to 80 years. So they can be very well mixed. And then what you also see that there are several these, bars, which shows that what forcing they put. So I'm showing what I just discussed in the previous table in a little more detail here. And that shows that what forcing they put on the top of atmosphere, that is in red, in the atmosphere, that is in the black, and the pink is at the surface. And what you notice that all these greenhouse gases warm the entire column, be it top of the atmosphere or in the atmosphere or surface, everywhere they are warming it, right? And that is why what we see that manifests into the global warming, what we are seeing. If you see on the right of this black line, you see particles or aerosols have a very short lifetime, going from days to week, and different kind of particles. For example, if you see the black carbon, it has a cooling on surface, warming in the atmosphere, and then warming on the top of the atmosphere. And likewise, what you see, other kind of particles have a different response. And that what makes it more challenging because of their shorter time, shorter lifetime in the atmosphere. So they are not fully mixed. Therefore, these numbers, what you're seeing on the right, basically are also very local, and these numbers can change from place to place. And that's why there is so much of effort going on to have more measurements and to get a better quantification of these numbers, what you see on the right of these black lines, so that we can better understand how aerosols influence the climate system. Now, just to show you that how these particles look like, and they could be very complex. I have just taken some pictures from what my student who was working on understanding a particular kind of, aerosol system, core and shell. And it just shows you that how, fascinating these could be if you expose them to very, highly resolved kind of imaging system. So what you see, there is a spherical particle, kind of spherical, not very much, on the left top of this collage. And then you see there are chain structure. Then on the bottom, you see there's a core shell, but the core has become collapsed inside. And then on the right corner, what you see is a very nice core shell structure. So this is a particle. The outside actually would have water and some salts in that. And within that, there is some kind of core sitting. And you see, these particles can have a very different response when they interact with light. So core shell structure, as I would show you some research that can actually respond to radiation in a very different way than what you see on the left corner, top corner, a pure spherical or mainly a homogeneous spherical particle would be. And then of course, these fractal kind of structure can be very, very complex when it comes to their interaction with magnetic radiation. This is just to give you another example. That was my another student who was working on understanding of how the dust particles interact with light and what's their optical properties, and subsequently how they force the climate. And these are again images which he obtained that time when he was doing PhD, I think sometime back in 2019, 2010. And you see that the dust particles can be large and can be highly non-spherical, which makes them far more challenging to compute their optical properties, which are very important to get a good idea about their radiative properties. And of course, he used some of the existing models, modified them, and he also developed some models. So you see that these aspect ratio is one parameter which gives you a good idea that how these particles are vis-a-vis the wavelength of the light they interact with. Okay. Now, from the direct effect, I was talking more about that, where aerosols directly interact with light. That's what we call so-called direct effect. Now I'm slowly moving to now indirect effect. Why it is important? Why we want to understand how aerosols interact with clouds, and subsequently how the clouds interaction with radiation can also exert some forcing on climate system. So this is a very classic plot. Basically, it is plotted by computing the Euler equation, which is said here, Euler theory. On the y-axis here is the super saturation, which is defined as basically 100 into saturation minus 1. So what is the, in percentage point terms, what is the excess water which is present in the atmosphere? And on the on the x-axis, you have droplet radius. And what you see that there are two parts of this curve. One is called the Kelvin effect, right? What you see, the solid line, and another is called a Raoult's effect. And these two effects are very physical effect, if you may. That Kelvin effect tells about the effect because of the curvature. So the smaller the particles, you have larger curvature, and that would allow the vapor to leave. So water vapor will try to condense on that because of very large curvature. It will just go back into the atmosphere. So that's what you see that on this part of the curve. If you go from peak to left side, this is a highly stable condition, so droplet would not form. And once it crosses this, inflection point, which is called transition point, then of course the droplet can grow because of this Raoult's effect. This Raoult effect is basically because of the salt. The salt which is present in this droplet, which is eventually becoming droplet, if you understand, that tries to minimize the vapor pressure, saturation vapor pressure. So these two are competing effect, and together they basically give rise to the formation of droplet. Just to give you an idea that because of the presence of these particles, a droplet can form at very slight supersaturation in the atmosphere, which is, as you see, this curve y-axis doesn't go beyond 0.1%. So that suffices to make the droplet, because the particles or aerosols are present in Earth's atmosphere. If in the absence of these particles, you would require few 100% of supersaturation, thereby there wouldn't be any droplet formation and no cloud formation. So from that point of view, you can understand that they are absolutely essential for the formation of cloud. Now, this is a very interesting work which was published in GRL very recently, that shows that if you were to remove all aerosols from the atmosphere, what would happen to the global warming? And if you just look into the first two plots from these 4 plots or 5 what is shown here, that shows that 4 or 5 different global models, which are shown in different colors here. These are 4 or 5 very established global models. And all of them show that if you were to remove aerosols from global atmosphere, you'll see there will be an excess warming ranging from 0.5 or 0.6 degrees C to up to 1.8. So you see that because of the overall, if you remember the curve, the plot I showed earlier, that where I compared greenhouse gases and aerosols forcings. And if you recall that on the top of atmosphere, aerosols have a negative radiative forcing and thereby they cool the planet. So some way they are offsetting the global warming, right? And if you remove them, it is just intuitive. And that's what the calculations show, that it could actually have additional warming, right? And which could go from even 1 to 1.5 degrees. So just imagine that in some way they are helping us by offsetting some of the global warming. So we saw that they are essential for cloud droplet formation. They are offsetting global warming. Are they also doing something else? This is a very interesting paper by Maria Kanakedu, which also is a very recent paper that shows that how aerosols can play a major role in moving nutrients from one part of these different, compartments of the global atmospheric Earth's atmospheric system by transferring these nutrients, be it nitrogen or phosphorus or iron, to the atmosphere. First, they are insoluble, then they can become soluble, and finally they can bring it to the ocean. So this whole thing is going on basically as a part of different biogeochemical cycles which is operating in the system. So, and this is also very, very important, because as you see that this connects the global atmospheric system to the global ocean system, and therefore it also has some role in the way that you have this overall balance of, you can say, the oxygen and carbon dioxide in this entire system. So that is another, you can say, is a important role that aerosols play in the overall global our Earth system, you can say, probably. So now I will just show that some of the work we have done related to aerosol indirect effect over Indian summer monsoon region, and that how they interact with cloud and what kind of impact they have on the Indian summer monsoon region by modifying clouds and thereby modifying the radiation. So before we go into that, I just thought that I will show this very classic picture that shows that aerosol interaction with radiation. That what is shown on the very left here. So that what you see, there are particles, and then electromagnetic radiation is coming. They can either absorb or they can scatter back. That is shown here. And then within this red box, you see there is a whole myriad of different kind of effects you see because of different kind of interaction that is going on between aerosols and clouds, right? So what you see, to just start with, you have a relatively clean atmosphere. There are few particles, and that's shown by few droplets that form. It's an unperturbed cloud, we can call, or it's like a normal thing. So we call unperturbed. Now, a famous Toomey effect, where you have larger number of aerosols. So of course, you have larger number of these small droplets will form. That's the second cloud as you move from left. And that, of course, can be shown that this would have larger reflections, right? A larger albedo. So cloud will reflect more, so that definitely will lead to more cooling. So that's called Toomey effect. And then now you have another set of effects, you can say, that now you have smaller droplets. So therefore, they will not actually coalesce and lead to large droplets, which can easily sediment out to form the rain. So therefore, what would happen that there is some kind of, we call like loosely a congestion of clouds. So clouds may hang in the atmosphere for a longer time. So we call it, for example, that there is an increased lifetime effect, then there is a drizzle compression effect, and all of them, all three what is shown here, could have different kind of impact on the overall energy balance, if you may, and also at the top of atmosphere radiative forcing. And finally, there is another interesting effect which was shown during Indian Ocean experiment, and then several other people also found it, which certainly cannot be directly observed, but certainly can be calculated. It's called a semi-direct effect, which actually mainly manifests by burning out the cloud. If you have black carbon kind of particles, and which is, of course, has to be coated by some hygroscopic material, and if on that some droplets form, then depending on its interaction with radiation, of course, it can lead to killing of the cloud. So that is called the semi-direct effect or cloud burn-off effect. So one thing what we did over India, because now you can understand that this souls are important, they are precursors to cloud. So from the prediction point of view, from not only understanding of cloud, but from how the clouds would form, how clouds would respond to changing number and composition of aerosols. One thing is that you like to measure something what is called cloud condensation nucleus, which is, or nuclei, which basically are aerosols over which a droplet can form. That is the definition of cloud condensation nuclei. You can certainly measure it, but measuring that is a tedious process. It's an expensive instrument. Certainly you cannot measure everywhere, as you know. So what happens that you try to measure it at some places, and then using certain theories, Kähler or improved Kähler, modified Kähler theory, you like to predict it, and you try to compare the observed versus the predicted, and that is called closure. And if you obtain a good closure, then certainly you have a very good idea about how the aerosols are behaving as Cesium, and then you can use this model to predict, basically in the regional models or cloud resolved models or even global models, right? So that is one attempt one of my students did long time back, where we had some measurements available from aircraft, airborne experiment we did in 2008 and 2009 over India. And what you see that on the x-axis in the right-hand side plot, where you see this pure ammonium sulfate is written. So we assume that aerosols are pure ammonium sulfate. We predicted it using a very simple theory for measurements which were available from different part of North India. All these places are mentioned here in the right bottom corner of this plot. And on the x-axis, you have measured Cesium. And what we found that, except what you see, these green symbols, Gaya, which is in Bihar, is a kind of eastern, not so east, but yeah, eastern state of India. Except that we have a reasonable amount of closure. So if you have a perfect closure, all of these points should really be lying on this one-to-one line, but that doesn't happen so easily. But what you see that based on aircraft measurements and in absence of chemical data, only you had the CCN measurement by CCN counter and CCN prediction using a very simple theory. We could actually obtain some very interesting results. Now, as a follow-up of work was done by one of my former students, Chandan Sarandi, who is now actually faculty at IIT Madras, where we actually looked into various cloud microphysical and macrophysical properties over Indian summer monsoon region. And this we look from the satellite measurements, which is shown here, that all these top panel plots are based on the MODIS data set, and the bottom panel are from MERA. So as you see, as you know, that MERA is a reanalysis product. And so basically you have corresponding, whatever is shown in the top panel, on the bottom of that is the same thing shown, but based on the reanalysis data, right? And what if you start from the very first plot, if you go in the very, in the first row and the very first plot, what is shown here is that on the x-axis you have cloud albedo, and on the y-axis you have cloud fraction. And this color coding is showing basically what is the optical depth. So if you have dark color, that shows you have high optical depth, which corresponds to high amount of aerosols in the column. Because optical depth, aerosol optical depth is a very important proxy for aerosols in the column. So what you notice here, interestingly, is that in both MODIS and MERA, you see the curve look very similar, that the cloud reflectance increases, okay, as you go for high optical depth conditions. Both the cloud reflectance albedo and cloud fraction is increasing. That means the cloud macrophysical property, because cloud fraction is related to the size of cloud. So the macrophysical property and reflectance is related to microphysical. Both are responding in a very similar fashion, that is cloud size is increasing and cloud albedo is increasing when you have more polluted scenario, right? And these are consistent in both. Now, second plot, what you see is on the x-axis, you have cloud top pressure and the y-axis is still cloud fraction. And you again see a very similar pattern in both B and G. So we have numbers here as well. I should have said that before. And again, for the polluted scenario, what you see that cloud fraction is increasing as the cloud top pressure is decreasing. So as you know, when the cloud top pressure decreases, that means that clouds are becoming taller. So what we are seeing here is that for polluted situation, polluted scenario over entire Indian summer monsoon region over a data set of about 2 decades, it's a large amount of data, and number of data, etc., are mentioned in CUC. N is equal to 1144. So it's a huge amount of data. And that again shows consistently that from satellite and from reanalysis data product, that for polluted scenarios, clouds are becoming larger and they are becoming deeper. And then the subsequent 3 plots shows that in a very similar fashion, they respond to the energy balance. So in all these 3 plots, what it shows that these polluted clouds cause larger cooling over the top of atmosphere. Without going into the details of these 3, now plot C, D, E, and H, I, J, which are following the trend, it shows that you have larger cooling over top of atmosphere. So that paper came out in Nature Communication. And what is going on here? So we just showed this using this cartoon. So if you see that on the left, what is happening is a clean, or if you may call it unperturbed cloud. You see you have a normal cloud which is formed here. You have smaller number of droplets. smaller number of ice particles. This is normal cloud. And now what happens that if you have a polluted scenario, you have more droplets, which of course would lead to more condensational energy that is being released that will fuel the cloud growth. So that you see that now clouds is becoming larger. Now more droplets are going up, and you see you have stronger arrows. So you have larger updraft because you have more energy in the cloud, so larger updraft. And that actually causes these droplets to go further. So they can actually form more ice particles. Now, ice particles can also release more, again, this condensational energy, and that could fuel even larger growth. And the cloud can actually cross this where you have these jets are going on. Okay, tropical easterly jet. That is that horizontal arrow. So what you're seeing here is that clouds are becoming bigger, they are becoming deeper, and you have larger numbers of these hydrometeors. And another interesting thing what we found, and that's shown in this paper, is that clouds have larger this deck, which we call as anvil. So mostly we looked into this into the CB clouds, cumulonimbus cloud, and we found that this anvil size also increased as a response to this large aerosol loading or basically high pollution scenario. And that, of course, what you see on the bottom, that we are showing that it can have also an interesting effect that could cause some, more stable or inversion-like scenarios, and that can feed into the climate, and therefore, over a period of time, it can also have some impact on buildup of monsoon in subsequent seasons. Okay. This also what we further looked into what impact it can have over the orographic clouds. And this is, I'm just showing by cartoon, which came out in this review paper. So this is on the very left, you have clean. So you have this windward, and you have leeward of a mountain. You have an unperturbed cloud. And for polluted cloud, now you have other mechanism now kicked in. So you have now droplets, more ice particles. So you can have priming effect, and you can also have this Wagner-Bergeron effect, which basically tells us that ice particle and the cloud droplet, when they coexist, then you know that ice particles can grow at the expense of cloud droplets, because the saturation vapor pressure over ice particle is lesser than over droplet. So basically, ice particle will eat out all the droplet and can grow faster, and it can really make the cloud go bigger. And what we found that it, of course, can also have some interesting impact on the rainfall in the mountains and in the foothills. So that was related to the indirect effect. Now I will talk about a little bit about the direct effect, that how aerosols can interact with radiation and what kind of then subsequent implication that could have on the climate system. So let me just start with this plot, which was created by one of my my first student, Dr. Sagnik Dey, who is at IIT Delhi now. And so he created this plot as a part of his PhD thesis because he was working on computing this direct radiative forcing of aerosols. And this work, as you know, that has been carried out by ISRO over entire India, and they have a very large program on that. What it shows basically that you see that from every location, that's the drawn out these arrows, you have these bars, and that shows that what is the forcing, and these are called forcing efficiency, that forcing watt per meter squared divided by the optical depth. So the unit doesn't change, but it gives you per aerosol optical depth what is the forcing. And that's a very good way to basically compare forcing across the globe. So what it shows that different places you have these, one bar is going up, so that shows the positive warming effect, and another is going down, that's over the surface. It has a dimming effect. Sometimes it's called cooling, but people also use dimming, was a very common name given to aerosol effect on the Earth surface. And if I just try to draw your attention that, for example, between Kanpur, you see these bars are very large. And if you look at Nainital, these bars are very small. You know that Nainital at 2.5 kilometers in Himalayas was certainly a much cleaner place in 2006. Maybe things are different. And now if you compare further, for example, in the Bay of Bengal, just close to Andaman and Nicobar Islands, you see these bars are still, again, very small compared to what I showed over Kanpur, where you have very high optical depth. So I discussed earlier when I showed those nice pictures, if you liked it, of aerosols. And one thing one of my PhD students did is that he tried to model by first doing measurement, and then he tried to model the optical properties of this core shell structure. So what you see here on the right, that this cartoon shows that you have only a soot kind of a black particle, it interacts with light. But if it is coated with a shell, so your black thing immersed into this brown, now the interaction with light could be very different, which could lead to more absorption, right? If it absorbs more, you really want to quantify it. So what he did, that he basically did a very clever experiment, that he used a set of two, particle sizing system, which is called scanning mobility particle sizer. And he could very accurately determine the thickness of this brown shell. And then he actually could very well model by using some chemical information of the shell and assuming that the black thing is black carbon. He used the core shell theory to actually compute what would be the amplification in absorption. And that is what is shown in this plot here. And one could see that for a large coating, you could have as high as up to 100% amplification in the overall absorption by core shell structure compared with only a core, black carbon core particle, and which was published in Environmental Science and Technology. And then now, as a follow-up to this, this student, Shamjad, who is, I think, working in probably somewhere in King Fahd University as a tenured scientist, he again looked into these absorption of these particles, mainly carbonaceous particle, and then he tried to understand that how their molecular, level chemistry is influencing it. So what you see that on the y-axis, these are information from mass spectrometer. You can get very accurate idea about hydrogen to carbon ratio, and y-axis and x-axis you have oxygen to carbon ratio. And these are basically, these are color coded with, and the color coding is giving you this E absorption is basically absorption coefficient at 405 nanometer. And from that also we drew some very interesting inferences from that. And he used them to compute, because once you compute the overall forcing from all the aerosols, then idea is that, as I showed earlier, that different type of aerosols have a very different interaction, and therefore consequently they exert the atmosphere by giving a different forcing, right? And that is what he did here, that this is the total aerosol direct radiative forcing for a clear and a biomass burning days. So you see that the blue bars show for the clear sky, and the orange bar shows when there was a large biomass burning event. And the same thing he could also compute for only brown carbon forcing, brown carbon aerosols. And interestingly, what we found that although the overall response was similar to the composite aerosols, but the cooling over top of atmosphere was relatively lesser. So that means that because of some of the brown carbon, and mainly in the UV to mid visible, or certainly up to mid visible, some of them absorb light, and that is why you see this kind of a very, very interesting effect. Okay, so now having talked about that how aerosols are important for offsetting global warming, how they play a major role in cloud droplet formation, and thereby then of course there is a whole plethora of effects they exhibit by modifying clouds, and then moving on to also showing that how they actually exert this direct, so-called direct effect. Now I'm moving to the final part of my talk here, is about air quality, health effect, and what kind of program the government of India has launched uh, mainly to mitigate air pollution in this country, that is India. So probably many of you are familiar with this slide, which was a work done by Jos Lilwild, and which shows that what is the overall mortality on the left-hand side uh, because of air pollution across the globe. And you see that over India, at least in this paper, it was shown that over India and China, there is a large number of premature deaths that can be attributed to air pollution. And most of that was actually linked for residential cooking sources, right? For at least for India, this blue thing shows is that residential cooking, that is people use the solid fuel, etc., which is causing the large number of premature deaths. So given that we all know that air pollution have some serious health related issues, I just want to show you that there's some interesting global measurements which are going on in probably a first attempt to have simultaneous chemical data collected across selected sites over globe, and that's called Spartan network. The main motivation of this network was to basically improve the predictive ability of PM 2.5, which is a surface parameter, using the satellite-based aerosol optical depth, right? That is the main objective, overarching objective of this project. But in that process, we also have got quite a few new learnings. I will just share with you some. So now this network is running across a dozen to 1.5 dozen sites across the globe. But when it started, there were 6 or 8 very well selected sites, and Kanpur was one of them. And you see, it's a very interesting system. It's quite autonomous. It collects particle also, and you have to, of course, take out those filters and try to analyze it. And at the same time, it also measures the scattering using nephelometer, and all this data can then be used for a whole range of purposes. So what you see, that one interesting thing, just to show that there are already, you see there are sites in Canada, in US, in South America, and of course over Europe and then Asia. And if you see that, if you look that these pies, the second rows of pies which show PM 2.5, and this information is for somewhere 2014. And over India, you see Kanpur, this number shows 93 microgram per meter cube, which is probably highest amongst all these sites. So the main conclusion from this site is that global simultaneous measurement-based PM 2.5 shows that, well, over India, we have the Kanpur, which is showing highest PM 2.5. So that's the main thing. There are other things, but certainly that you could see in this paper. And then very recently over Delhi NCR, we did some interesting measurements. You know that you could do some chemical assays of these particles, and which gives you a very good idea, which is called as reactive oxygenated species, which can tell you the adverse impact these particles can cause to human lung cells. And these are basically called oxidative potential. So higher the oxidative potential, the more dangerous these particles are for human health. So we found that we could get this information from Delhi from online measurements, and then we could compute their oxidative potential, and then you try to apportion them in various sources. And this can give you accurate information about how how or to what extent these aerosols impact human health. And that's how also you can try to mitigate or prioritize these mitigation of sources. So given in this backdrop, India launched National Clean Air Program in 2019. And I'm just showing you that what kind of efforts the institutes of higher learning, mainly the technical institutes and the national labs are putting to support this program by the way of developing new monitoring systems, new monitoring technologies, also helping them by doing some real-time source apportionment using these real-time chemical speciation measured, and then also source apportionment of these reactive oxygenated species so that one can also prioritize these source mitigation by looking at their health impacts, because you can also prioritize them based on the economic consideration and their health, and of course you have to optimize it in some way. So this Clean Air program, of course, was launched, as I said, and in the first phase, about 132 cities have been selected. And the goal is to cut down PM 2.5 in these cities by 30%. And that is by, as you see that it's mentioned that by prevention, control, and abatement of air pollution. And this whole program actually sits on three pillars: by increasing knowledge, by creating more institutional capacity, and then try to mitigate, plug the sources across all major economic sectors. And in these 1 and 2, where I'll be talking more that in what way we are contributing to the efforts of National Clean Air Program. So one network, an alliance of technical institutions we have created, which is called National Knowledge Network. It is recognized by government, approved by government, and this has been created mainly to bring all the expertise related to air quality which is present in the country, so that they can be assigned to each of these cities at a local level, and they can provide continuous technical inputs to the cities so that they can certainly improve the way they are implementing National Clean Air Program. And this is basically the structure I just thought I will show you that how it works. And as of now, over India, we have, as I said, that these stars show all these institutes, which we call institutes of repute. And you see they all are basically in the vicinity of these circles most of the time, which are non-attainment cities. That is the cities which do not adhere to currently the national air quality standard. So as of now, we have about 19 institutes of repute who are connected with this network. And in some way, they all have some kind of a collaboration going on with these 132, 133 non-attainment cities. So I said that there are 2 or 3 ways by which we are trying to help implementation of National Clean Air Program. One of them is basically working with the sensor-based air quality monitoring. You know that currently in India, there are about 700 to 800 monitors. Out of that, 600 are or 500 plus are the manual monitoring systems, and remaining are what they call it continuous air quality monitoring systems, which are very expensive. So given their cost and the fact that they are all imported, they certainly cannot, they alone cannot meet the monitoring needs of the India's air quality or India's air quality monitoring needs. So given that, we also have started working on some alternate technologies which can supplement, complement this monitoring program of in India. So this is one work which actually in collaboration we did with Duke University, where we looked into accuracy and precision of sensors, which was published a couple of years back. And we found that across 2 or 3 locations in different environments, if you can have good idea about, the sensors, how they are responding to the PM 2.5 for different temperature and RS. So if you can have control on them, or you can actually incorporate them into calibration model, you can achieve an accuracy of up to 8% compared to equivalent reference grade monitors. That was one of the important finding in this work. We also then did this similar exercise for gas sensors, and there we actually used a little advanced machine learning tools, and we tried to do it for NOx and ozone. The left plot is for NOx, the right plot is for ozone, and we could see that for ozone we could actually get up to 15% accuracy compared to these reference grade gas analyzers. So these are two very interesting things, and these results also were consistent across two different cities, Delhi and Mumbai. A follow-up work we have done in Mumbai, where we have put sensors. It's a field evaluation in collaboration with Maharashtra Pollution Control Board, which is the chief regulator, environment regulator of the state of Maharashtra, where we spread out 40 sensors across 15 CEA QMS, the government monitors. And we tried to look into sensors accuracy and also whether a model, calibration model developed at one site can be adopted to another site. And we found that with the limited co-located data, we could definitely do some model transfer from one location to another, and that was published in IEEE Sensors. So now, just to scale up these efforts, currently we are in the process of deploying sensors network in the city of Delhi. In Jaipur, Mumbai already we have done the field experiment, then we are going for Chennai and Kanyakumari, Navi Mumbai and Thane, and then we also we have plans to extend these networks in the rural India, because we know that air sees no boundary and rural air quality also is deteriorating quite fast in India. So that is one way we are contributing to National Clean Air Program efforts. The other way is that you want to also in a very precise way and in an efficient way, you want to understand sources which contribute to pollution, PM 2.5. And there we have used some of these real-time measurements, real-time complete measurement of PM 2.5. And using that, this is a very summary overview of all the results we had from about 2 years of measurement, which led to about 1.5 dozen papers. And this is summary information which tells you that how we can attribute ambient PM 2.5 to different type of sources which are just listed here. Okay, and some of these information or some of these infrastructure we also use to understand sources during the lockdown over Delhi, when the COVID lockdown was imposed from 3rd week of March through June 2020. And that time the chief regulator of India, Central Pollution Control Board, was very keen to understand how the sources have responded to this lockdown when most of the economic activities were mainly brought to a halt. And that time, for different phases of lockdown, because we were getting complete speciation of PM 2.5, we could give these information, what you see here for organics, for inorganics, and also for black carbon. This entire information is given for different phases of lockdown, and this information was very useful for Central Pollution Control Board. So I think I have just 2 or 3 slides more. I'll be concluding very fast. Another very interesting thing, certainly for Delhi NCR, what we did was that if you have the high frequency data, in this case the metadata, you can combine that with the wind, and that can give you accurate information of the geographical location of sources. And that is what is shown here based on the measurements conducted over Delhi in 2018 and 19 winter, you see that different kind of these, particulate matter, which are linked to different sources, are basically coming from very, very different directions. For example, for cluster 1, they are coming from northwest. For cluster 2, they are coming from both northwest and southeast. And cluster 3 again is coming from northwest, but it also somewhat further going into a little across the borders. And this is now this work is not published yet. This is a work which is basically led by my former student Deepika Bhattu, who has joined IIT Jodhpur now after having a long stint of postdoc at PSI. She has been trying to look into this. The idea I talked about is the oxidative potential, which is directly linked with the adverse impact of PM on human health. And there she is trying to go deeper into that. She's computing this oxidative potential by mass, oxidative potential by volume, and then you can do more than one chemical assay. That is what is listed by these three approaches: DCFS, DCFH, AA, and DTT. And then she's trying to understand that how these approaches combined, what information they give you about these particulate matter and in different season, winter and summer over Delhi. And more interestingly, this is a very crowded plot, but I just want to tell you that each of these bars actually have 5 bars, correct? And these 5 bars show 5 different sites over Delhi, and they are going for different months. So if you see on the top, January, February, March, April, May, January, February, March, April, May, and that repeats for 3 different kind of chemical assays. One is that AAV, second is DTV, and third is DCFH. So for 5 months, 3 different kind of assays to get the chemical oxidative potential across 5 sites, and the color shows that what is the contribution from different kind of sources. So these are sources, the colors are shown on the top. And the key conclusion from here, what you see is that large contribution to OPV comes from organic aerosols, more from secondary organic aerosols. So these are very, very interesting and new information. Again, what it says that for elemental sources, major contribution is coming from copper and cadmium rich sources. So these are something very, very crucial information for policymaker, so that then if this information comes out, they certainly would like to go and cap or plug these kind of sources which have disproportionately high impact on human health. And finally, I'll just stop on this slide that this is earlier a work we did related to Taj Mahal discoloration, that we know that the iconic monument of Taj Mahal in Agra city of Uttar Pradesh, the province I live in, was, getting routinely, it required cleaning for its outer marble surfaces. And it was not very clear that what is the reason, the source, not the source, what is the composition of the muck that causes this yellowish color of these outer marble surfaces of Taj Mahal. And by doing some very interesting sampling, chemical composition, and developing some kind of model of opacity of the particles which deposit on Taj Mahal surfaces, we could clearly apportion them, and we found that the most of the discoloration is because of are equally, you can say, equally split between dust and carbonaceous aerosol, and that was a very interesting thing, and that was this was taken into cognizance by government, and then they tried to bring some new policy measures and enforcement so that further degradation, further discoloration could be stopped. So yeah, I mean, I'm happy to stop here now.